Hi guys, Dr. J here, and in this video I want to just go through an example with you in Colab of how you might look at some data and start to look at the autocorrelation and the variogram associated with that data. So what we're going to do is we're going to use a data set, which is actually not a geologic data set, but I think it's pretty interesting. It's the COVID-19 data set that's available from the New York Times, and we'll look at the state of Missouri. So this is a GitHub repository. You can access the data here, and I'll have a link to this notebook posted on Canvas so you can access it as well if you'd like to look at it. So we're going to look at the data, and we got lots of data, lots of different states. I'm going to go ahead and just pull the Missouri data. Okay, so here's our Missouri data, and the number of cases, we can plot those. All right, so I'm going to go ahead and plot this, and now you can see it's plotting the total number of cases. I don't really want to look at that. I want to look at the daily rate of cases. So I'm just going to use the NumPy gradient function to take the gradient of this curve, and that's just going to take the gradient assuming that a one-day measuring rate. All right, now we seem to have a little outlier here. This last day in this data set is pretty high. I'm guessing that's probably an artifact or some kind of outlier. So I'm going to go ahead and get rid of that and assume that that is probably something that needs to be corrected in a future version of the data set. And I'm going to go ahead and rerun this. There we go. Now I've just replaced the very last data point with the one from the day before. That looks a little bit better now. Okay, so here's the daily rate of COVID-19 cases in Missouri, state of Missouri. So we're using Pandas to read this comma delimited file, and Pandas allows you to parse dates. So I've told it which column is a date column, and so it's parsed that as a date time object. I can then set that as the index of this data frame. So I've read the CSV file into a data frame called COVID-19. I can look at the type of that file, and if I come down here, notice that I'm setting the index of that data frame to be date. So now you can see that this date now, instead of having these integer index, we have a date time index. So when we do that and we say plot, we'll plot the number of cases. That's going to give us our date time on the x-axis. And that's what we want to do here as well. So I'm going to go ahead and run this. All right, so now we see the number of cases through time per day, the daily rate of cases. Now, there is a caveat here, which is that I haven't really checked carefully that every single day has a number of cases. It looks like it probably does, but if there were some missing dates or something like that, then my derivative would be a little bit off. I'm not going to worry about that for right now. For demonstration purposes, we'll just go with it. Okay, so as I was saying, this is a time series plot. Value of rate of cases per day through time, and there is some correlation structure here. So you kind of see this gradual increase and then a gradual decrease. You see superimposed on that overall structure, there is some kind of noise in addition to that. So let's look at the autocorrelation of this time series. And we can do this very easily in Pandas. There's a few things that we're going to look at here. The first thing we're going to do is look at the correlation between a couple of different delta times. So in other words, we're going to make a lag plot. We're going to use the Pandas plotting module and the lag plot function. And it's going to take in a series, which is just a column of a Pandas data frame. And we're going to plot it for a given lag. So lag equal to 1 means it's going to take a lag of 1 day in this case, because our time series are daily time series. So we're going to take a lag of equal to 1, and that's shown here in this plot. So what this is saying is it's going to take each value in this column and plot it on the x-axis, and on the y-axis it's going to plot the value for the next day. So you can see that these are very correlated. So if the value on one day is close to 0, the value on the next day is close to 0. There are no cases here where the number of cases per day goes from being 0 to more than 1,000 in one day. And that's what you would see if that were the case. We could fit a line through this plot and compute an r-squared correlation coefficient. And that r-squared is exactly the autocorrelation, the value of the autocorrelation function for a lag of 1 day. Let's look at a lag of 5 days. Well, we can look at this 10-day one here. So what you'll tend to see, as I said before, is that the correlation decreases with an increasing lag. So here for 10 days, Now you see there's much more scatter. I can put these both on the same screen, and you can see here there's pretty tight correlation right around the slope of line with the slope of 1. Here there's quite a bit more scatter. So for example, on this point right here, you go from a value of about 2,500 cases in a day, or 2,600, up to a value of more than 6,000 cases within 10 days. So this is showing you that the variability is greater for a larger lag. And I can do a few other values here. Let's look at lag is 5. So we're, again, more scattered than lag of 1, but less scattered than lag of 10. I can go to lag 15 days, and the scatter is greater yet. Now if we go to lags of very large numbers, and right now I'm showing 100, let's go to 20. You see the variation starts to get larger. So this is, 30 days from now, what is the rate of COVID-19 cases going to be? And it's almost impossible to say. So for some days, the rate of cases is actually much lower than it was today in 30 days from now. And in other cases, 30 days from now, the rate of cases is much, much higher than it was today. So we have this whole range of uncertainty here when we're looking 30 days out. As we continue to increase our lag, we get to a point where we're basically uncorrelated. So there's no relationship, or very little relationship, between what's happening now and what's going to happen in 50 days from now. We can also look at the autocorrelation plot itself. And this is, again, something which Pandas allows us to do very nicely when we have a time series data with that date-time index. So we can use this autocorrelation plot. And again, we're looking at the daily rate. And here it is shown right here. So for different lags, and you see again these lags that I was using, 50 days, 10 days would be over here. Here's 100 days where you're basically at 0 correlation. Some negative correlation actually at 200 days. But this is our spatial structure function now. So for example, we might want to forecast. And so we could very easily forecast COVID-19 rates out even 10 days from now, just based on this structure function. We could forecast dates up to probably about 50 days from now with some degree of accuracy. Once we get out to more than about 60, 75 days, we're basically at 0 correlation. We would not be able to use this time series, even though we sort of see this long-term trend, we couldn't use it to predict the number of cases 100 days from now. But we could use it to predict the number of cases 10 days from now, and we would probably be pretty accurate. Okay, so that's just a little bit about a little example on spatial autocorrelation using Pandas and Python, and I will see you in the next video.